It's a pleasure to speak to this conference and to see in this indirect way all my friends in Ukraine. I wanted to first tell you a little bit, but some of you know it, tell you a little bit about my connections to Ukraine. And of course, I was born in your, what is now your country, except when I was born, it was Poland. When my mother was born, it was Austria-Hungary. So it's a part of the world that has changed. I wanted to show you part of that connection, in particular with Lviv, because by showing you something from history, this is the little booklet which records the grades of my father when he was a student at the Lviv Polytechnic. Our name when I was born, our last name was not Hoffmann, but Safran. And his name was Hillel Safran, and he was born in Latsky Male. I was born in Złotów. And this is the card, this is the document that he had when he was 20 years old. You can see the date in 1931, when he entered the Lviv Polytechnic. I wanted to show you another historical picture, and it's the following. He was a civil engineer. He learned at Lviv Polytechnic how to build roads and bridges, small ones. And here was one of his first jobs, which was to build a road, to supervise the building of a road near Lviv. The building was done with machines in part, but in large part by human labor. What's interesting about this picture is that, first of all, this is a picture of my mother and father. It's taken in the year I was born. And what it shows is mixed technology. That is, my father was using machines to build the road, supervising that. But when he wanted to show his young wife, they are both around, in this point, 1937, they are 26 years old. When he wanted to show his wife where he was working, of course he took a horse and carriage, because you could not drive there. So this is the kind of technology that was used. Anyway, I think this establishes the connection which has persisted to this time. But I want to talk about the subject of my talk, which is nanostructures, which is your talk. My approach comes from a academic chemist point of view, from a point of view of knowledge of basic subject matter. And it is, as was shown on the first slide here, based on an article I wrote a few years ago in Angewandte Chemie, with a lot of help from a talented postdoc who was working on this with me, Xiaodong Wen, who has since that time become a very successful chemist and entrepreneur back in China. It is about the lessons that we can learn from chemistry for nanoscience. Now, let me say a few things in general. Nanostructures are popular. They are somewhere between fashion and revolutionary substance. And they have come to fill the popular scientific, science fiction, and patent literature. There are commercial implications, but for the large part, they are on the way. The field is indeed very nicely interdisciplinary. It has inputs to it, as you just heard, from materials, biology, chemistry, and human expertise from just all over science. The level of hype is extraordinary. That is, I think it's pretty clear what I'm saying. Much more is being promised than what has been done. And you have a unique situation where the natural tendency of scientists to exaggerate the importance of what they are doing is coupled to the natural tendency of journalists to increase that. One has to watch against that. But there is also substance, this intermediate scale of structure and dynamics of matter, so long neglected in all of the sciences, chemistry, physics, especially, is being gradually filled in. Very little is known accurately or precisely, and that's a good thing because there is a lot of opportunities. Also, it's fun, as you have seen. Let me start a little bit with cartoons, because I came into the field only in part and rather late. And what I saw first in the work of my colleagues were cartoons like these. So this is a typical cartoon from the literature for how you make nanoparticles. You do it either bottoms up, and there's a picture of atoms or clusters, condensing, or various variations on this, like vapor deposition, condensation, and there is a top-down approach where somehow you subdivide the material, whether it is by ball milling or by etching or by sputtering. In some way you make the nanoparticles. This picture is a cartoon, and it's okay to present it in a lecture to a high school audience, but it should not be taken too seriously. More realistic is the kind of picture which you see at left in this slide, where somehow some source of the, let's say it's making metal nanoparticles, where some solution of some metal salt is then reduced biologically, chemically, in the presence of some solvent. And what you get is these pictures you see in this cartoon of nanoparticles, of solvent and metal particles, which aggregate, accumulate, and eventually you get the nanoparticles. What's the difference between this cartoon and the previous one is mainly in what is on the little bit on the outside of the particles. That is, there is some ligand, or there is something that's stabilizing it. The reason this is absolutely essential is that, of course, if there were no ligands, the thermodynamic sink is the aggregation of the little pieces of matter back into the stable form that it has of bulk metal or some semiconductor or some ionic substance. I'll come back to this again. And I think one cannot overemphasize the need for good organic and inorganic chemistry in the design and study of the ligands. The bad thing is that most of the visualization methods that we have, like various X-ray spectroscopies or transmission electron microscopy, of course respond to the heavy metals. And so people begin to look at the pictures of the nanoparticles and they begin to think that there are no ligands there. But without those ligands on the outside, and I call them ligands and not surfactants or anything else because I want to make a connection to inorganic chemistry. Without those ligands, the particles would not exist. I think a lot is to be done on studying the inorganic chemistry of the stabilization of nanoparticles by ligands. And I would like to refer you to what I think is the very best work in the area, which is by a young person, an associate professor at Columbia University, Jonathan Owen, who has worked out many of these things in detail. I just want to mention one problem, for instance, that there is. In a study of semiconductor particles like cadmium selenide, which I'll get back to in a moment, we have things like amines or carboxylic acids, which coordinate as ligands and stabilize the acidic sites of the nanoparticle, which are the cadmiums. But we don't have many ligands that coordinate the basic sites of the nanoparticle. So the ligands themselves have to be Lewis acids, have empty orbitals, and we need more Lewis acids. Let's talk a little about stability because this enters the field. As chemists, we know the difference between thermodynamic and kinetic stability. We have this basic picture of a barrier, and even if the water wants to flow over the dam, there is a dam, there is an activation energy to be overcome. Nevertheless, while we know this difference between the words stable and unstable, usually referred to thermodynamic, and the words persistent and reactive usually refer to kinetic, referring to the size of the barrier, we tend to use the word stable colloquially, and it's perfectly okay. I just want to get into focus the difference which the education of chemists and physicists introduces into the common sense meaning of the word stable. In general, to chemists, from the beginning, stability is, if a teacher has done their job well, is mostly kinetic and a small part thermodynamic, whereas the word stable for a physicist usually means mostly thermodynamic and relatively little kinetic. Where the difference is introduced is this. All of you have had the experience in an introductory chemistry course or at secondary school or in college, and someone brings you a hydrogen balloon and puts a match to it, and it explodes. And everyone says, ah, wonderful, it has exploded. Well, yes, that is, why has it exploded? Because the thermodynamic driving force for H2 plus O2 going to water is there. But of course, the miracle is that that balloon will not explode until you put a match to it. That is, there is a barrier, which is what that match starts, a autocatalytic chain reaction that leads to that explosion. But it is the overcoming of a kinetic barrier that is essential here. I have to wave my hands because the light in my room goes off every once in a while. Just to make a point here, to persist as a solid in the air, to be available in a bottle, to be viable at 1 atmosphere and room temperature for a day, a molecule has to have an activation energy of 15 to 20 kilocalories to reaction with anything around it, and in particular, if it's going to be a solid, to dimerization. This is often forgotten, so let me make the point for you in another way. This is something very simple. This is diatomic molecules, homonuclear diatomic molecules, lithium 2, boron 2, C2, N2, O2, F2 in a solid curve here. What is plotted here is the atomization energy. That is the bond dissociation energy. And all of you know what is at the top of that curve. It is N2, the most stable diatomic we have, with a bond dissociation energy of 228 kilocalories, 10 EV, however you want to put it, in whatever terms, 1,000 kilojoules. These are, N2 is very stable. So here is a list of all homonuclear diatomics. At the top is N2, number 2 is C2, number 3 is O2, number 4 is in the second row P2, which has over 100 kilocalories energy to knock it apart into 2 phosphorus atoms. And what I want you to ask is, which of these molecules do you have in a bottle? Which of these molecules have you seen? And the answer is N2 and O2. You have not seen any bottle of C2 and P2, even though it takes 140 kilocalories to break apart C2. The thermodynamic stability of C2 has nothing to do with its viability. C2 is reactive. It is a diradical. It goes on to give eventually graphene. Yet we have all seen C2, but not, we've seen it in a very strange form we don't think about. The blue flame in hydrocarbon flames. The yellow is due just to soot particles, and that's black body radiation. The blue part is an emission from C2 and from OH radicals that are formed as intermediates in hydrocarbon flames. Anyway, thermodynamic stability is not as important as kinetic force. So to continue to make this point, are the following stable? A carbon atom? Yes, but of course, kinetically, no. A carbon atom is as hot as anything in the world can be. It reacts with absolutely everything. C2 reacts with absolutely everything. But carbon in the form of graphite or diamond is thermodynamically stable or metastable by a little bit in the case of graphite, but a little bit of pressure will shift the equilibrium to diamond. C60 is very interesting. Some people think C60 is absolutely the world's best material, and you can do chemistry with it. It's kinetically persistent, but thermodynamically very unstable. If C60 were cheap, you could heat your house with C60 and get more energy out of it than if you could heat your house with coal. H3 plus, a beautiful triangular molecule, is the most abundant form of hydrogen in the universe. But you've never seen a crystal structure or a complex of H3 plus, an inorganic complex. The reason is that H3 plus, even though it's thermodynamically stable with respect to H plus and H2, is very, very reactive. It is so reactive, it transfers a proton to absolutely everything under the sun. Let's look at sodium chloride, because that gets us closer to nanoparticles. We know what sodium chloride is. It's a cubic crystal with a rock salt structure and with a separation between the sodium and the chlorine of 2.846 angstroms. NaCl diatomic molecule exists. You can laser ablate it from the surface of a sodium chloride crystal. It is very reactive. Per sodium chloride, it is 2 EV uphill from the solid. One thing, though, that's interesting is even sodium chloride is very reactive. It's not particularly kinetically persistent. It's not. But I want you to notice something. It has a 4.45 angstrom shorter distance. And usually we associate short distance with more stable. So there is something to think about. After what I tell you more, you'll see why sodium chloride diatomic, even though it's not stable, has a shorter bond. And you might think a stronger bond. It does have a strong bond, but it doesn't matter that it has a strong bond. It's very reactive. That was the story of C2 and P2. If cut out of the most stable form of a three-dimensional solid, I'm now going to use colloquial language because I'm a teacher, and the if I know how to translate it, believe me, into professional language. But unless I tell it to you in colloquial language, it will not stick. If you cut out of a stable form of a three-dimensional solid, for instance, sodium chloride, any molecule piece like NaCl diatomic, or a tetramer of that, doesn't matter. If you cut out of that on paper any molecular piece, of course you are going uphill in energy. Any such molecule will be hurt, to use colloquial language. It loses some of the bonds that it had to it in the crystal. And of course it will try to heal itself. Molecules are not stupid, only the human being studying them. Of course it'll try to heal itself, which is another way of saying that it will, if possible, subject to the constraints of what else is around in temperature. If you're at liquid helium temperatures in a noble gas matrix, nothing will happen. It'll sit there and you can study it. If it's in interstellar space and subject to no collisions, the H3 plus is there. But if it comes near something else, it will try to get back some of the bonding that it lost. It'll react with itself or with solvent or air. That's what happens to H3 plus or carbon atoms. And or it'll adjust the bonding to stabilize itself. Now, for the case of sodium chloride, which I just mentioned to you, the diatomic, here is the sodium and the chlorine and the diatomic, and they have just one neighbor of an opposite charge in an ionic picture. But they have orbitals. So what they do is they turn on the bonding, which was saturated in the solid. But when you have the diatomic, you have a lone pair in a 3p orbital on chlorine. You have an empty 3p orbital on a sodium. The two will form a pi bond. Actually, there is some pi bonding in diatomic sodium chloride, and that is why it gets to a lower distance. Okay, now I'm going in the wrong direction. In surface science, these adjustments I've mentioned of healing itself, they are given fancy names. They're called relaxation and reconstruction. There is no sharp division between these. Relaxation means just a little bit of motion to adjust. Reconstruction means a more major type of motion, which may involve the motion of atoms. Let me give you an example. Here's silicon. We're now in surface science, but we'll be back to nanoscience in just a moment. Silicon, the stable form, has a diamond lattice. You can see that in the picture, right? And along comes a human being and makes a clean cut. That's the red line on that silicon surface. Cutting in this particular cut in such a way as to cut two bonds to other silicons at the top. So what you see when you cut out first in the so-called unreconstructed surface is at the bottom of the left. This is a top and a side view, And I think you see the solid state structure, so you can connect up in your mind, and you can see that the dark lined atoms are the ones which are in a darker yellow or brown in the top picture. So those have at this point two dangling bonds, if your knife is sharp enough to do it. And so what they do is they, of course, heal themselves. So what do? They bend over to the neighboring silicon and form a bond to it. That's this symmetric structure, which you see in a side view. And you will notice that it actually is the three coordinate silicons are still pyramidal. It's not a good situation. Actually, it adjusts even more. And this is a very interesting reconstruction of the surface where the two silicons do not remain symmetrical, but one goes up and one goes down. It's not obvious how that makes a better bond, but it actually does. But this is an example from surface science, and these things have been studied by various physical methods by surface scientists. And what they have learned, and this is the purpose of this talk, is an important lesson for nanoparticles as well. Let me give you another example here, which is actually the way I got into cadmium selenide and nanoparticles. Cadmium selenide exists in two forms, diamond structures like that of cubic and hexagonal diamonds, sphalerite and quartzite structures, essentially a diamond lattice with alternate atoms, cadmium and selenium. There is a rock salt structure, which is a high energy structure, but under pressure with just a few gigapascals, that is of the order of about 50,000 atmospheres, cadmium selenide goes over toward the rock salt structure. We'll come back to that. I got into this as in a collaboration I had with a very good Korean scientist, Taekwon Hyeon, one of the leading nanoscience people. And he was able to make some nanosheets, which were interesting because he could make consistently, reliably around platelets of cadmium selenide, about six atoms, 6 layers thick. And he showed them to me, and he showed me these pictures, which you see at right. And here is where I, an outsider, fell for the cartoon. These pictures, which are transmission electron microscopy pictures, do not show the ligands that, in fact, are responsible for the stability of these platelets and which are responsible for the kinetic barrier that this material has to going back to bulk cadmium selenide. So the moral of this is, do not show such pictures to innocent people like theoreticians without telling them that you're not seeing everything, that you're seeing just what my instrument sees. We actually studied this. We did something nice, but I don't have time to tell you about this. What I want to show you is from some calculations that we did that were associated with this. And unfortunately, the pictures here are small. But I want to show you a microscopic detail, what happens to a surface when the surface is created, and then when it is passivated, when something comes on it. So we start out with a quartzite structure for cadmium selenide. That's based on a hexagonal diamond structure. And that's a structured left. We modeled it by a 4-atom layer, which was passivated on the bottom. But I want you to focus on the top after we optimize. At left is the structure before optimization. At right is the structure after this in a theoretical calculation, you have to trust me, the structure after optimization, not much happens except to the surface layer. I'll come back to that. The bulk layers remain about the same. And what happens to the surface layer is not easy to see until I point it out. But let me point it out at the bottom. You see here in the unreconstructed structure of that surface, the purple here, or blue, is the cadmium, the green is the selenium. You see this in this cut out of the solid, the selenium remains pyramidal and the cadmium next to it remains pyramidal. I go over to the surface. When I allow it to relax, look what happens. The cadmium goes planar on the surface, every cadmium. But the cadmiums underneath don't change. The selenium goes, that's not obvious, actually more pyramidal than it was. And the distance goes down a little bit. This is the sodium chloride story. There is some better pi bonding in this adjusted structure. Okay, now I'm going to bring up ligands to the structure. We are going to see in microscopic detail what Lewis bases, which is what was actually used by our collaborator, and Lewis acids, which no one has good ones. There are a few studies with aluminum trichloride, but let's see what they do. So here is what happens to that surface when every cadmium on that surface is approached by an ammonia, the actual molecules that were used to stabilize by the Korean collaborator we had was an octylamine, but here modeled by an ammonia. And what you see is that the cadmium goes pyramidal again, and selenium stays pretty much the way it is. Now, one of the nice things about theory is you can do things which you cannot do in experiment. And one of the things that you see in this slide, again, it's hard to see, but in the original paper you can see it better, is we've passivated every coordination site on the surface. So every cadmium has acquired an amine as a ligand, and every selenium has acquired BH3, a borane, as a ligand. That's very hard to bring about experimentally, but that's one of the good things about theories. You can do that. The net result is a sterically crowded surface. This is not going to happen in reality. But what happens very briefly is the cadmium-selenium bond returns to pyramidality. It returns to about the length, if you could follow this, that it has in the original structure. So what we've gone through is a process of healing of the cadmium selenide surface by reaction. The activation barriers for ammonia approaching that surface and for borane approaching that surface are zero. That is, these are spontaneous acid-base reactions, now, what does that mean about a cadmium selenide in reality? You put cadmium selenide into a solution of some sort. What this is telling you is that cadmium selenide surface, when you make it, like it or not, is going to pick up any dirt that you have. And dirt means molecules, chemicals. Of course, it picks up hydroxide and protons if you have them around. And those are natural things. One of the interesting things about the cadmium selenide story is actually you can make a stable compounds some of those coordinated surfaces that I just showed you. Those coordinated surfaces I showed you, sorry, I have lost my place again. Those coordinated surfaces I have showed you are not stable. They're theoreticians' constructs. But here, Jing Li at Rutgers has remarkably made molecules, inorganic molecules that are crystals, whose crystal structures you see here. So they're stable enough to do a crystal structure. And what these are, as you can see, is there are two-dimensional layers of zinc telluride, in her case, very much like cadmium selenide, zinc telluride stabilized on top and on bottom by amines. And here, by amines that bridge from one layer to another one. Remarkable things, also with very interesting electronic properties, nanostructures or quantum objects, which I haven't talked about. The band gap is tunable in the case of these molecules that she has made, which are different layered structures of different topology. The band gap can be tuned across the visible, so there's obvious applications. I wish I could tell you more about it, but you can read about it in Lee's work. Let's talk about dimensionality, which comes up here. So here are some carbon nano objects. Buckminster fullerene at left, a zero-dimensional object, by which I mean a molecule, a nanotube, a graphene layer, and diamond. Now, yes, one can see those in certain circumstances, and you have seen them too. But usually you get them as aggregates, though you can see the single objects under certain conditions. As aggregates, what they are crystal of Buckminster fullerene, and next to it is a typical jumble of nanotubes, which comes from a nanotube synthesis. And then you see graphite or Bernal graphite here, AB. With now, we tend to still see the objects as 0, 1, or 2-dimensional. And what is behind that is an assumption, which I have written down at the bottom, and that is that there is a big jump from the intramolecular to the intermolecular separations. That jump being exaggerated by the physical methods we use for visualization. Take a look again at that nanotube picture that you see here. Each nanotube in this picture is maybe 20 angstroms across. We are not at atomic resolution. They are single-walled nanotubes. And then it's lying next to another one. Why is this method of visualization showing the things as distinct nanotubes when the electron density is actually falling off? Because the electron density falls off exponentially outside of the bonded region into the region between the nuclei, or because there is a big jump from intramolecular to intermolecular separations. You know what they are. In graphite, the distance is 1.40 angstroms between carbons within the layer, but the van der Waals contact, dispersion force induced, slightly attractive interaction between the graphenes is over a distance of 3.3 angstroms. So there's a big difference between 1.4 and 3.3. The difference is a bond and no bond. So it's okay what we say. Sometimes it's not so easy to define intramolecular, intermolecular, or to define coordination number. So let's talk a little bit about that. In liquids, there is a way of defining coordination number sometimes. This is a typical kind of thing you get for a liquid from X-ray or neutron scattering. This is for lead, as it happens, liquid lead, and it's a radial distribution function. So the horizontal axis is distances, and this is the probability of finding a pair of atoms at that distance. Nothing happens until you go to a little over 3 angstroms. Then there's a large probability. And then typical of a liquid is that there is a first coordination sphere, a second, and after this is going to go flat. There is disorder. This is typical of a liquid. People have defined the first coordination sphere by, it's clear, pretty clear, that you should draw a line between the two the two peaks over here, the first and the second, and then you would get a certain distribution function for that. Sometimes it's not so obvious where to draw the line. The drawing of the line for the liquid was where there was the largest gap between peaks. Okay, here is a square lattice. Here is the nearest neighbor contact. This is the diagonal of the lattice, and the next one is twice the unit cell. The largest gap in this is a histogram of distances in a square lattice. The largest gap is right where I'm pointing right now. And it would make you think, if you go by largest gap, that a square lattice is 8 coordinate. That's crazy. We think of it as 4 coordinate. It's sometimes difficult to define coordination numbers from a histogram, but the histogram has the fullest information. There is another way of looking than a histogram of distances, which is very informative. And this is an electronic dimensionality. And what's interesting, and I wish I had more time to tell you about it, is that there is a way of defining dimensionality from the density of states in an electronic band structure. So if you have atom here, the p orbitals of ethylenes, cyclopropene, all the way benzene onto a larger, you spread out a level into a band. And you can read more about this in a book in which I've collected 2 articles about solids and surfaces. Atoms spread out into a band when they aggregate. There's a picture right that we sometimes draw like this. Turns out that when the delocalization of the electrons occurs in one dimension, very characteristic of them is a spike in the electron density called Van Hoff singularity. When they are 2-dimensional, it turns into a square. And when it's 3-dimensional, it's more like a parabola or gently rising in some way. You can get all kinds of shapes from superposition of this. But when I see a density of states without knowing anything, the fact when I see a sharp rise, and then that looks to me like the middle one of these, I have an idea that there is 2-dimensionality in this structure. So this is another way. And what's very interesting is those cases which come in more frequently under high pressure, where the electronic dimensionality differs from what you would conclude on the basis of structure. They are few, but they are very interesting. Okay, we're back. I had this slide before. I talked about molecules that are hurt, healing themselves by reaction or relaxation or reconstruction. I want to show you a few of these because they're sort of fun to see with respect to nanoparticles. So here is the way to think electronically about relaxation or reconstruction. If you have a stable solid, say at left, say a semiconductor, cadmium selenide, in a diamond or a Wurtzite form. And it has some filled levels, it has some unfilled levels, it has a substantial gap. Diamond is transparent, cadmium selenide is red. Supposing you cut out a cluster of it. Now, that's not the way you make the cadmium selenide nanoparticles. You don't take a knife and carve out a cadmium selenide, but it doesn't matter. This is a hypothetical paper construction. If you were to take a cadmium selenide cluster, a naked cluster, then what would happen is you would hurt it. Translated into orbitals, that means that some levels go up in energy and some levels will go down too, but the filled ones will go up. What you get is some picture like this in a naked cluster, some levels which have been pushed into the gap. This is the source of the reactivity, both as a base, the filled levels at high energy, and an acid, the empty levels at low energy. And then the thing desperately tries to heal itself. If it has nothing to react with, if it has something to react with, it uses these orbitals. A cluster is both a better base and a better acid than the thing it was cut out of. That's another translation of what I have here. And then as the cluster relaxes, it finds some way to stabilize the orbitals, but it never quite gets back to as good as it was initially. So that's the electronic picture of relaxation reconstruction. The question you ask is how much? Well, it depends on the bonding capabilities of the surface. And here are the important things. And here I cannot give you anything except generalities. There are some general rules of thumb. On metal surfaces, I'm reading here at the bottom of the slide. On metal surfaces, if you have high index planes, for instance, an FCC 111 plane, where each atom, which was in a metal was originally 12 coordinated, remains 9 coordinated as you cut away a layer. In those high coordination surfaces, not much reconstruction will take place, some relaxation. If you have an open plane where you have cut a metal so that just a few atoms remain on the top, they've been hurt a lot. They'll do something. It's obvious they'll do more than the other planes. Semiconductors, there is also in general much reconstruction, especially if, again, atoms with low coordination numbers and with strong bonds are exposed, like in carbon or silicon. In ionic compounds, there's generally small reconstruction, and they remain a fragment of the solid. Let me show you an example for sodium chloride. Here's sodium chloride. These are calculations again. Rock salt structure. I cut out a diatomic molecule. It's 2 eV above the numbers here are stabilization energy relative to some arbitrary zero. The monomer is 2 eV per sodium chloride relative to rock salt. You take a dimer, it goes into a square, and it's regained almost 1 eV. So it's exothermic with no activation energy to dimerize. The trimer, it's better if it's like that. The tetramer goes into a cube and doesn't want a ring. It really likes this is driven, as you'll see, largely by metal-lung energy. It really likes the fragment of what it was. As you go on, you slowly build more. As you build larger clusters, you have more and more, but you're still largely fragments of a solid. This is an amusing one. This is a solid, a cluster, which has been designed to maximize the surface area, or to, if it's been tortured, to maximize the pain of having been cut out of the solid maximally. Yeah, it rearranges a little bit, but not by much. And very quickly, other clusters are favored. And eventually, one-dimensional ones, rock salt is in this energy scale, minus 6.31, a linear chain, sodium chloride, a one-dimensional structure, is almost an EV above it per sodium chloride. You really is not very good. Two-dimensional ones are a little better, not much. Here are the three-dimensional structures. One interesting is for sodium chloride, of course, the rock salt structure is favored, but zinc, blank, and wurtzite, which are the favored structures for cadmium selenide, are above it, but not by much, by about 0.15 EV. That's just 3 kilocalories per sodium chloride. But as you go to other higher coordination structures like cesium chloride, at least at ambient pressures, that doesn't work. Here's an amusing slide. This is the energy of 47 clusters and arrays we have calculated. 0 dimensions are molecular ones. You've seen them. 1 is the diatomic molecule. 44 is rock salt sodium chloride. Of course, it's the most stable. It better be. And then these are various. If you stay in 0 dimensions, you can stabilize, but there is a limit. Of course, if you build a lot, it depends on the number of atoms, because if you allow the thing to grow three-dimensionally, it'll go toward this. But what's interesting is that you can get the atomic formation energy of the optimum size of the cluster by doing a simple Madelung calculation with a charge on each sodium and chlorine, but not of 1, plus 1, and minus 1, but of plus 0.85 and minus 0.85, which may mean that the charge definition is just not very good for the parent system. Cadmium selenide is more covalent than sodium chloride, but less covalent than silicon or carbon. And you remember what has changed. Now the zinc, blank, and wurtzite structures are more stable than the rock salt one for cadmium selenide. They've reversed relative to sodium chloride, and it remains reversed for diamond and silicon. And now, if you look at the nanoclusters, they're amusing. Here are some optimized structures for cadmium selenide nanoclusters. They're very different for the small clusters. But you go to the larger clusters, like number 4 here, lower right, and you'll see that the structure is really like that of bulk cadmium selenide, just reconstructed on a surface, melting on a surface into some favored structure. So I think this is, you can see here why surface science is instructive for thinking about nanoparticles in terms of restructuring and reconstructing the surface. I now come to the end, and there are just 5 things that I want to leave with you. I have told them already. The first idea that I want to leave with you is that clusters and nanostructures are molecules. And by being cut out of a more stable solid, even if they're not formed that way, they are inherently metastable. The chemistry is what I'm prejudiced in favor of chemistry. I should say my daughter has a PhD in physics, so I'm respectful of physics as well. But I think that chemistry is at work here. Nanostructures are reactive. I want to leave that with you. Naked nanostructures are desperate to be stabilized. You need to pay attention to inorganic chemistry and stabilizing them. And thinking the chemistry need not be complicated. Just think of acids and bases, donors and acceptors, though I've given you also an electronic way to thinking about it. The same ideas that work for thinking about the stability of individual molecules work for nanostructures. They do have remarkable electronic properties, but they do not seem to affect their reactivity very much. The fourth and next to last thing in this list is that since cutting them out of a solid is a construction principle, it gives you, it stresses the importance of surface science, of ideas of relaxation and reconstruction, which I take to be a contribution of surface science, that these are useful. The last thing I think should be obvious. Please do not divide chemistry. Nature does not recognize that you are an organic, inorganic, solid state, or surface chemist. These are all molecules. They are of different dimensionality, and they need to be studied, but they obey the same laws. Thank you very much for listening. It's been a pleasure to tell you this story.
Thank you very much for your nice presentation. We have a lot of participants who was able to listen to your lecture and on our YouTube channels and in the conference hall. And now we have questions which came to us by email. One of them is, how do you think, what is nanostructure such as graphene, oxide graphene, cadmium selenide, or other, will be the most promise for industry in the nearest future? What do you think? What nanostructure will be mostly promising for industries?
That's not a question to ask for me because I'm here a basic scientist. I will say something about graphene oxide. Then in the Middle Ages, people named diseases, and they had the same sicknesses we have. And at some point, they assigned names to the diseases. And they also assigned certain devils to, with certain names to be responsible for them. And then they felt more comfortable. None of that helped to cure the disease. One of the diseases of scientists today is to give names to things they don't understand, and to think that by giving them names that they have understood them. I find graphene oxide to be one of these things. I want to know, as a chemist, what is graphene oxide? Now, I understand, I know what it is. It's dirt, it's oxygen-heavy, dirty graphene. But I want to know the nature of the dirt. I want to know the number of epoxide oxygens, to be specific. I want to know the number of OH groups. I'd like to know the disposition of the OH, the H, and the epoxide oxygens on a graphene surface. So, but none of that has much to do with the commercial ability. So, you are asking me a question by asking that question, which to me seems about as deep as a question of what should I invest in the stock market today. I cannot tell you what is going to be useful. I don't want to be negative. I have infinite faith in the ability of chemists to come up with things that are valuable for society making life easier and healthier for people. But I cannot tell you uh, what to work on. What I can tell you is try to find out and tell me how many epoxides and OHs there are on a graphene surface. I cannot tell you which of these is going to be more commercially available.
Okay, thank you for this question. And I will ask participants from conference hall, maybe someone, one moment. Someone, do you have the question? Okay, yes, yes. Він виключений. Там він не працює. Підійдіть сюди. Працює? Do you listen?
Especially nanoscience and your prediction of possibility.
I cannot hear.
One moment, I will ask.
You will have to repeat it, please.
Okay. Сідайте.
Maybe I'll ask you're here from this position. Maybe it's yeah. Okay, so thank you very much for your nice talk, nice lecture. So my question is more maybe philosophical. What do you think? Is it thermodynamically possible? A lot of people say about possibility to organizing of a nano machine which will be work, for example, instead of people. How do you think? Is it possibly thermodynamically? Is it thermodynamical rules allow us to predict possibility to organize inorganic nanostructures as a real machine like we have in our Dimensity world?
Yes. So that's an interesting question. And a very specific, for instance of this kind of machine is it possible, for instance, to design a molecule in which one part of the molecule rotates in one given direction rather than in the opposite direction? And given that it's a quantum system, I think it's possible. I think there are interesting interplays with basic questions in quantum mechanics, whether at the really microscopic level you can determine some basic things happening in one way or another way. But in general terms, I think it's possible to design machines that work on the molecular level and that are efficient in some way. What you will not be able to design is things that violate the second law of thermodynamics over globally. But you can perhaps, I think, design machinery, molecular machinery, that operates fairly complex tasks, and which also, and this is the most interesting part, is that the interplay of electrical and mechanical energy transmission took a long time for human beings to evolve. The idea of an electric motor that you could make, that was only invented about 150 years ago, 200 years ago, rather. And I think that in molecular machines, the coupling between electrical and mechanical energy transmission is more direct and more intimate. So I think this is the area in which we will have greatest advances, where you have a change in pH or an applied external voltage, and it causes some mechanical transformation at a microscopic level, which then can be scaled up into a macroscopic motion. I think the greatest advances so far come in from organic chemists and the field of mechanochemistry and the work of people like Fraser Stoddard or other people in designing molecular machines. They are mostly organic, but at some point they will begin to be inorganic.
Sir, thank you very much. One maybe remark concerning of this. So, is maybe I have to concentrate my question on a entropy factor. So, is it possible to go through the Maxwell-Diamond problem in this case? So because from the entropy point of view, maybe the effective transformation of electrical energy and fields into mechanical motion. I'm not sure that it's so easy to go through this barriers, through this Maxwell diamond of Maxwell problem. Yeah.
Yeah.
No.
I don't have any. I don't have enough knowledge. I have read some of the papers, but I don't understand them very well.
I'm sorry, but maybe.
So I don't have an opinion, really.
Yeah, okay, I'm sorry. Okay, thank you very much. Thank you, in any case, thank you very much. But...
And we have two last questions. One of the whole, I will invite because our microphone discharged. That's why I must invite. And one from the chat. So two last questions and we will stop.
So hello, and thank you very much for your talk. I have a question again relating to where one should invest. I'm sorry for this. As you know, physicists have been doing this ultra-high vacuum experiments on metal and semiconductor surfaces already for very many decades. And we always try to achieve an atomically clean surface. Then physicists investigate reconstructions on top of them. How do you think, is it worth pursuing this trail of studying the surface reconstruction? Or actually, I myself, and I think many other physicists would agree with me, they have found hardships in the recent years, finding the funding for such kind of experiments, which are extremely resource consuming. So what is your opinion? Do you think it's worth going on further this road?
Yes, I understand your problem in the funding, and it's no different in the United States. In general, the level of funding for ultra-high vacuum studies of surfaces, of surface science done at low pressures has been decreased. And I have had friends who have worked in that area who have suffered from this. These are the studies from which I learned these ideas. These ideas I gave you. My picture of the silicon surface reconstruction, for instance, silicon the 2x1 reconstruction on silicon 100 came from studies from high vacuum studies. Very expensive to build these machines, and yet they provide very basic information. I still think that the most important ideas for studying higher pressure reactions come from these low pressure studies. And I think they're very, very important for our basic science understanding.
Okay, thank you.
Keep on trying.
Thank you very much. But maybe just a short follow-up question. Should we perhaps now believe the theoretical calculations instead, like DFT, with this universal periodicity and these slab models, because it's much simpler to conduct these numerical experiments nowadays?
Yes, so the theory has gotten much better. There is another story about the numbers being more reliable, and that is across the board from properties of molecules in interstellar space all the way to the reconstruction of metal surfaces. I think the theory has become better. What bothers me, and I have just discussed this in 3 essays in the last issues of Angewandte Chemie, what has bothered me is that the concentration on experiment, especially the recent flood, the concentration on numerical calculations, especially the recent flood of artificial intelligence type things like machine learning and neural networks, are building a picture that that's where understanding resides. And there is no understanding that comes from that. All that comes is good numbers. So there is, to me, where understanding resides in what I can teach to a student in words and equations. And if the person tells me to see how that surface reconstructs if I change silicon to germanium, I have to do a calculation, then I would say they don't understand this. So I am here on very contentious ground on what artificial intelligence means for our society. And I am worried, even as I love the idea that you can trust the calculations. I think you can trust the calculations today, done in the hands of good people. I am worried that those calculations will take in the minds of people the place of the actual understanding.
Yeah. Okay. Thank you very much.
Thank you.
And the last question from the chat. This question will be read Oksana because she can see this chat. I cannot because I am in Zoom. And it will be the last question.
Yes.
Many thanks for excellent talk again. This question came from Dr. Leonid Dolgov. Dear Professor Hoffmann, are there any known ways of stabilization of nanoparticles by physical way, like some nanomanipulators by atoms in microscope, which allow to stabilize those which is unstable?
Could you repeat the beginning of what you said? Please read again.
Are there any known way of stabilization nanoparticles by physical way, like some nano manipulation by atoms in microscope, which allow to stabilize molecules?
It's clear that what you need to do is to avoid collisions with themselves or with other things, or to make the collisions harmless in some way. And that we know, for instance, that you can get tremendous information on unstable molecules, on kinetically reactive molecules, by putting them in at liquid helium temperatures in a neon matrix. So matrix isolation at low temperatures is a way of studying things. You can still do spectroscopy on those things, but you heat up the matrix and the nanoparticles react with each other. The other way to study them is while they are flying down a molecular beam and not making many collisions. And again, you can do various spectroscopies. Those are the only ways I know, not of stabilizing, but at least of studying them before they disappear.
Thank you again, and we must to move to the next speakers, and I hope that it will be not the last our meeting, and I hope that we will have opportunity to have meetings in the future face to face, and maybe you will come to us the next year. Maybe COVID will be stopped. I hope. Yes, and we have a lot of other questions. But we must stop because we have 3 other presentations. I will try to send you this question by mail and people who ask this question. Okay, and do you remember that we with you discussed possibility to have small clip about developing of science in USA and in Ukraine. Maybe we can discuss in the future what practical ways we can to try to use best practice to use in Ukraine. Yes, to use in Ukraine. Thank you a lot for your presentation, and see you in the future.
See you. Goodbye.
Bye.